Welcome everyone. I am so absolutely thrilled you're joining us for today's explainer because, well, we're going to be looking at something that is completely invisible, yet incredibly powerful. We're talking about electricity. It is quite literally the invisible force that powers our daily lives, drives human progress, and keeps this whole modern world running smoothly. But what exactly is happening behind those wall sockets? What is the secret life of this energy? Today, we are going to unpack exactly that by looking at the incredible effects it produces when it actually moves.
So I want you to just imagine waking up tomorrow to a world completely without electricity. No lights to flick on when it gets dark, no fans to keep you cool, definitely no mobile charging to connect you to your friends, and zero television for entertainment. It's kind of hard to even fathom, right? Electricity is unarguably one of the most important discoveries in human life. But what is actually flowing through the walls to prevent this dark, quiet reality from happening? What actually happens when you flip a switch and electric current rushes through a wire?
Okay, let's dive into this. The definition itself is surprisingly simple. Electric current is really just the flow of electric charges through a conductor, like a copper wire. Think of it kind of like water flowing through a pipe. But instead of water, it's a massive rush of tiny, invisible electrical charges moving from one end to the other. And here's the crucial part. When this current passes through that wire, it doesn't just quietly travel from point A to point B. It actually produces very specific, highly usable physical effects in the real world.
Which brings us to our agenda for this explainer. We are going to look at the dual superpowers of electricity. Number 1, the heating effect, and number 2, the magnetic effect.
Superpower number 1, the heating effect. So when electric current flows through a conductor, that conductor actually becomes hot. Electrical energy is literally being converted right there on the spot into heat energy. Just take a look around your kitchen or your living room. We use this specific heating effect in so many of the everyday appliances that make our lives comfortable. Electric irons, room heaters, your morning electric kettle, your toaster, or even the geyser that heats up your shower water. Inside every single one of these appliances is a special wire. It's called a heating element. And when the electric charges flow through this specific element, it becomes incredibly hot. You're literally harnessing the invisible flow of charges just to toast your bread or press your clothes.
But you might be wondering, how do we actually control how hot it gets? I mean, we definitely don't want a toaster that melts your kitchen counter, right? Well, the amount of heat produced depends on 3 very specific factors. First up, the resistance of the wire. Higher resistance means more heat. Second, the amount of current flowing. A higher current is going to produce more heat. And third, the time for which the current flows. Obviously, the longer you leave it on, the hotter it gets. By perfectly balancing these 3 variables, engineers can give you an electric heater that beautifully warms a room or an iron that gently smooths out a silk shirt without ruining it.
And this brings us to a classic example you're definitely familiar with: electric bulbs. A traditional incandescent electric bulb contains an incredibly thin wire called a filament, usually made out of tungsten. Now, why tungsten? Well, because it has a ridiculously high melting point. When the electric current rushes through this filament, the heating effect is basically pushed to the extreme. The tungsten becomes so phenomenally hot that it actually starts glowing, producing light. That is our intended outcome. But there is a wasted byproduct here. Not all that electrical energy becomes light. A lot of it is just wasted as pure heat, which is exactly why those old light bulbs get so burning hot to the touch.
The heroic sacrifice, the electric fuse.
Now we've talked a lot about how useful the heating effect is, but it can also be incredibly dangerous. If a wire gets too hot, it can easily start a fire. That's exactly where this ingenious little safety device comes in. A fuse is intentionally made of a wire with a very low melting point. It's literally designed to be the weak link in the chain. Let's walk through it. Step 1. Suddenly, too much current flows through the circuit. Step 2. Thanks to the heating effect we just talked about, our low-melting fuse wire immediately heats up. Step 3. It gets so hot that it actually melts and snaps. Step 4. The circuit is instantly broken. The flow of electricity completely stops. By sacrificing itself, the fuse brilliantly protects all your expensive appliances from damage and prevents terrible fire accidents. It is a disaster entirely averted using the exact same physics that caused the threat in the first place.
Superpower number 2, the magnetic effect. Now, what's really interesting about this is that it introduces something that feels almost like magic. When electric current passes through a wire, it doesn't just create heat. It also produces an invisible magnetic field completely surrounding the wire. This incredibly serendipitous discovery was made by a man named Hans Christian Ørsted. He simply observed that a standard compass needle, which naturally reacts to magnetic fields, would suddenly twitch and move when it was placed near a wire carrying an electric current. The flowing charges were literally creating magnetism out of thin air. No way, right? But it's true.
And this specific discovery led to one of the most important inventions in human history, the electromagnet. Basically, an electromagnet is a temporary magnet. You make one by passing electric current through a coil of wire that's been tightly wound around an iron core. The absolutely crucial word to remember here is temporary. When the current flows, the iron core suddenly behaves just like a powerful magnet, but the very second that current stops, the magnetic effect completely disappears. This is brilliant because it means their magnetic strength can be entirely controlled just by turning the current up, down, or off entirely.
Because we can turn this magnetism on and off at will, we literally use it everywhere. The magnetic effect powers tiny everyday tools like electric bells and the loudspeakers inside your headphones. But it also scales up to power massive industrial machines, like those giant cranes you see in junkyards that use massive electromagnets to lift entire cars, and the huge electric motors that power modern factories.
Let's move to and see how this builds into a true masterclass inside an electric bell.
Let's look inside an actual mechanical device you probably use all the time without thinking about it. Now, this cycle happens incredibly fast in real life. Step 1, you press the doorbell switch. Current flows. Step 2, the coil instantly turns into an electromagnet and attracts a little iron arm called an armature. Step 3, as that armature moves, a hammer attached to it violently strikes the metal gong. Ding! Step 4, but the moment it moves to strike, it physically breaks the electrical circuit. The current stops. Step 5. The electromagnet instantly loses its magnetism, so a tiny spring pulls the armature right back to its original position. But wait, returning to its original position reconnects the circuit. The current flows again, the magnet turns on, the hammer strikes, over and over and over incredibly fast, producing a continuous ringing sound. It is just a perfect, rapid-fire kinetic loop of electricity and magnetism.
And you know, it's not just bells going back and forth. Electric motors take this exact same magnetic principle and use it to spin. An electric motor essentially uses the magnetic effect to convert electrical energy directly into mechanical energy. It's the spinning heart of the fans keeping you cool in the summer, the mixers in your kitchen, the washing machines cleaning your clothes, and the water pumps keeping your whole plumbing system working. So we've really unpacked the secret life of this incredible energy today. The next time you plug an appliance into the wall, I want you to stop and ask yourself, is the invisible current rushing inside there right now heating up a wire to warm your home? Or is it creating a temporary invisible magnet to spin a motor? The entire modern world is built on these two incredible superpowers of electric current. Thank you so much for joining me on this explainer today, and as always, stay curious.